All right. What you want to pay particular attention to is this this big gap in the center. The big gap in the center means this empty space. This empty space is called void space, and so this will be an example of a cubic void. What we can do is we can make more complex crystals based on this. More complex crystals would be something like cesium chloride. Take a look at cesium chloride. Do you see the greens? The greens are kind of the simple cubic, but in that big space there's an ion, the cesium ion. And so a more complicated structure can be built from a simpler structure by putting an atom right in the center. So go ahead and put an atom right in the center of that.
Different color?
Yeah, different, a smaller one. Something that fits. And so do you see how which one is bigger, the cations or the anions?
Anions are bigger.
Anions are bigger. And so if we put the chlorides as the big ones here, and then the cesium is the smaller one, then that's the cesium chloride structure. Do you see it? Okay. All right, now that's different than this. Okay, look at this structure. And see, this structure looks just like the cesium chloride structure you built, but the difference with this structure is all the atoms are the same. We don't have a small cation in the center, and so all the atoms are the same. This would be an example like magnesium metal. All the atoms are magnesium. And so the next structure you're going to build is body-centered cubic.
How's this from
the same?
How is it different? All the atoms are the same size. If you try to put the same size atom in the center of your crystal, it doesn't quite work. It needs to expand a little bit. In other words, here, do you see the atoms touch?
Yes.
Do they touch here? They don't touch. Different.
So we use one of the same size.
Where the atoms touch is important. Let me show you why it's important. Because remember when I was talking about the unit cell? The unit cell turns out to be a perfect cube. If it's a perfect cube and it repeats, then what has to happen is we have to slice and dice the atoms to fit. And so if you see a corner atom, a corner atom, only 1/8 of this corner atom, this wedge, is in that unit cell, in the brick. Only 1/2 of a face atom is in the brick. An internal atom is completely in the brick. If there's an atom along the edge, only 1/4 of that atom is in the repeating brick. And so in order for this to stack properly, we have to slice the atoms in half. Otherwise, they don't stack properly. They're not the repeating unit. So did you guys build the body-centered cubic? Now, a simple cubic like this has a very low packing efficiency. We can calculate the packing efficiency. That is, calculate the volume of occupied space versus the volume of empty space. Do you know how we calculate that? Let's go back to this diagram here. If you look at this, this is the simple cubic structure here. And if you add up all these wedges, how many atoms can we build? One atom. Because there's an 1/8 wedge on each corner. And so if we add these up, we have one whole atom. One whole atom is 4/3 pi r cubed, the volume. And so we know the volume occupied by the atom. And then if we know the volume of this cube, then we can calculate the percentage of occupied space. That is the volume of the atom divided by the volume of the cube. The volume of the cube is not difficult to calculate. Here, it's equal to 2 times the radius because the atoms touch along the edge. Or we measure it. And so it comes out to about 50, a little more than 50% occupied space, close to 50% empty space. Oops, where was I? All right, what you just built is called the body center cubic. The body center cubic is going to be in the 60% range. Because how many atoms do we have here? Well, we have one atom from the corners plus one whole atom in the inside. So it's 2 times 4/3 pi r cubed is the occupied volume divided by the volume of the cube. Now the volume of the cube is very tricky because the atoms touch along what's called a body diagonal here from these 2 corners. And so we have one radius and then one diameter and then one radius. And so there's 4 radii along the body diagonal. But anyway, calculating the occupied volume, it's in the 60% range. The next one we're going to build is the face-centered cubic. So you're going to build it 2. This is why you need 2 kits, and don't get the balls mixed up. You're going to build the face-centered cubic cell, and you're going to build the face-centered, what they call the CCP lattice.
Can we see an image?
This is called the face. Let me show you an image. This is called the face-centered cubic lattice here. Unit cell. They just color the atoms differently.
So in the face center, there's nothing in the center?
There's nothing. The very center of this is empty.
Yeah, so there's no statements. It's a hogging.
Get the right template, and then you're going to build something called the cubic closest packing diagonal, something like that. For the cubic closest packing one, you're going to need the spacers, the plastic spacers.
Wait, is it the same template, Dave?
No, it's a different template.
Can you let us know?
Did somebody find it?
This one here. No, this one face center. C.
Look at the instructions because it tells you what layers. Like layer 0 is a spacer, layer 1, layer 2. And that's how you stack the balls on. So take a look at the instructions.
Is this the cubic closest?
Yeah.
This is the cubic closest.
Yeah, face-centered cubic, body diagonal.
In the middle.
Do the face-centered cubic, body diagonal.
Oh, this one?
So what?
This one.
Why are we doing this one? How's it different? How's this two different?
Plus what?
How this two
Yeah,
different?
different.
How these two are different?
This is space center cubic. This one. Body down.
Are we doing this or this?
There are 2 of them. Build both of them.
This
So
is
you
both
build
of them.
one or build. Okay, I'm building this one. I'm building the bottom.